Thank you for the opportunity to be potentially a part of the University of California, Irvine Medical Center's OshPod Cup expansion project. This design presentation is Team OCCPEP2's approach for what we consider an out-of-the-box solution to truly separate the OshPod infrastructure feed at the campus.
The first element of our proposed project is the provision of a new central plant on the southeast side of the campus. A new sustainable building incorporating natural daylight and easy-to-maintain building materials will be constructed and sized to accommodate 4 1,000-ton chillers and associated chilled water and condenser water pumps. The plant will include a new 1,000-ton chiller and 2 existing 1,000-ton chillers relocated from the existing modular chiller plant. The relocation of the chillers will be in compliance with OshPod published PIN 55. New 18-inch chilled water piping mains from this new central plant will connect to the existing 12-inch chilled water piping currently serving the Douglas Hospital and will continue as a new 14-inch chilled water piping to connect existing buildings 1A, 3, and the future emergency department expansion building. The central plant will also have 3 new cooling towers with a provision for a 4th tower to support the proposed 3 chillers and future 1,000-ton chiller. New 12 kV normal and emergency transformers, 40-volt switchboards with a new transfer switch will be provided to meet the power demands of the proposed central plant. The design also incorporates new efficient cooling towers sized to 76-degree wet bulb at 93-83 condenser water temperatures and equipped with high-efficiency mist eliminators and low-noise fans to minimize both drift and noise on the south side of the yard. Our proposed central plant design eliminates the need of routing 24-inch condenser water piping to the existing modular chiller plant, reduces the pipe size to 18-inch chilled water supply and return, and associated electrical feeders and conduits are reduced in size. It also consolidates all mechanical central plant equipment in one location. The design minimizes shutdown of the existing central plant systems by keeping the existing modular chiller and associated cooling towers in operation while the proposed central plant is constructed. It provides ease of construction and phasing, as almost all the construction activities are dedicated to the south side of the central utility plant yard. This solution provides easy access for maintenance and operation, with increased clearances around the equipment. Our design also provides space for a 4th chiller and cooling tower with expansion capabilities in the future to add a 5th redundant chiller and cooling tower if needed. The design also frees up space on the north side of the yard for future electrical and mechanical equipment by removing the existing modular chiller plant and associated cooling towers. This could be used for a future 6th emergency generator on the north side of the yard. The chilled water connections to buildings 1A, 3, and the future emergency department expansion building and conversion of existing 5 kV normal and emergency systems to 12 kV system are an important element of the project. We've carefully sequenced and phased these activities to minimize interruptions to the campus. Our proposed design replaces the existing old transformers inside building 1A rather than provide additional 12 kV 4160 volt transformers outside of the building to improve both efficiency and minimize maintenance. Our design minimizes equipment outside building 1A by placing equipment inside building and provides dedicated switches equipped with vacuum interrupters to isolate individual transformers in building 1A. The provision of G&W switches with vacuum interrupters in place of fuse switches will improve reliability and ease of switching and maintenance. Power interruptions will be minimized by replacing 1 transformer at a time while keeping the 2nd transformer of the double-ended substation operational. The existing 5 kV switch in building 3 will be replaced with a 15 kV switch, and taps will be adjusted in the existing dual voltage transformer to facilitate connection of the Building 3 substation to the 12 kV system. A new SCE transformer, main switchboards, and transfer switch will be provided in Building 31. New duct banks and manhole for proposed SCE switches and replacement of the existing 750 kc mill feeder with a new 1000 kc mill feeder by SCE will be coordinated to minimize interruptions and energize the 12 kV system on schedule. Along the north side of the cup yard, a new 15 kW, 12 kV emergency generator will be provided south of the existing generators. The generator will be equipped with a neutral grounding resistor, particulate filter, and fuel storage to match the existing generators. A new outdoor rated 15 kV emergency switchgear section will be provided on the north side of the existing 15 kV modular switchgear enclosure that will accept the feed from the fifth generator, have breakers for emergency feeders, and a control section that will integrate with the existing master controller in the existing emergency switchgear. The provision of this dedicated 15 kV emergency switchgear avoids relocation of the existing batteries to accommodate the new section for the fifth generator, eliminates seismic and OSHPOD recertification compliance issues involved with the existing 15 kV emergency modular switchgear, and provides expansion capabilities in the future to accommodate the fifth generator.
A new wall will visually screen the MEP yards from direct view. Comprised of burnished face CMU with an upper 4 foot of simple louvered metal screening panels, it will incorporate planar breaks in its alignment as well as landscape elements to break up its length. The louvers will allow sunlight to cast finely scaled shadows, adding simple and ever-changing points of interest atop an otherwise utility and background campus feature.
We will now share our proposed design for the utilities that are being provided to meet the chilled water, oxygen, and normal and emergency electrical demands of existing buildings 1A, 3, 31, and the future emergency expansion department building. Our design utilizes a common trench to route chilled water and oxygen piping and normal and emergency electrical infrastructure to the subject buildings. The work will be undertaken in phases to minimize open trenches and keep a single lane open for through traffic. Our design also eliminates expensive boring through the central portion of the campus and uses the savings towards building a new central plant for the campus.
This concludes our presentation. I look forward to continuing the dialogue with the University of California Irvine Medical Center. Thank you.